Good morning, everybody. Good morning. Okay, I'm so delighted to stand here in front of you. I'm the first session of the second day moderator. My name is Ameria from Tanzania, East Africa. My professional is a mapping officer and land surveyor. I have a bachelor in geoinformatics, and I have a master of science in GIS. I work with the Ministry of Lands, Housing and Human Settlement Development, like 16 years now, in the land field and in the mapping experience. Today, I'm going to share my geospatial experience, where I'm going to link the geospatial and basically in the space technology with the groundwater resource management. Please let us listen to one person or presenter online. The name is Hafsa Ayman from China, University of Wuhan. Please, Hafsa, we are on time. Please welcome and proceed. Thank you.
Thank you. Thanks a lot. So let me start with my presentation. So the topic of my today presentation is more about the assessing vulnerability of agricultural dependent communities to the climate change impact on groundwater. So today I'm going to present a case study in one of the district of Pakistan, which is Okara. And this presentation is going to have a kind of vulnerability assessment related to groundwater while integrating the factors of exposure, sensitivity, and adaptive capacity that we have implemented for this approach. Next, please. Okay, so the content of my presentation is split in a way that in a first component, I'm going to tell you about my research work and its significance, and what are its objectives behind it, and what are the materials that are being implemented to carry out this objective, and what are the results and how they're contributing toward the assessment. And lastly, I'm going to discuss with the way forward. We're working in developing the kind of groundwater management information system. Next, please. So about the climate change and geography of Pakistan. So the area that Pakistan is actually possessed is 796,000 square kilometer. And this area is also the summer monsoon accounts like most of the time with around 60% of its total area with received annual precipitation. And third-fourth of this country receive rainfall of less than 250 millimeter. And this region is also known as the sixth most populous country, and more than 37% of its area comprises with urban and settlements. And this area, like due to climate change, is now like more sensitive to the climate change threats that we have been facing from the past few years. Like we have the drought, then we have the flood, and how these variations in climate change are actually impacting the agriculture related sectors to it. Next, please. So what we talk about the climate change impacts on rural communities. So yes, they exist when we have a rise in temperature, when we have the extreme events. So in that scenario, then the water scarcity come that is being gradually increasing. And this is like one of the potential, the phenomena for the many regions. For example, in the case of Pakistan, when we have the kind of insufficient volume of water and we actually do not have idea about when and where we need to use it. So like in that scenarios, when we talk about the farmers, they are the main respondent who are actually been impacting due to this climate change. And yes, their livelihood associated to it, so that is definitely also impacting. Next, please. So about as far as my research significance is concerned, so my research significance is going to have the following objectives in terms of its impact. Next, please. So in research significance, we are taking the area of like Pakistan we are working on. This is only like already the water stress region and highly susceptible to the adverse effect of climate change, and as well as the economy that will actually depend on it and how its natural resources are being affecting due to it. Next, please. So my research significance is going to indicate what are its impact on agriculture productivity, and most importantly, the groundwater challenges that we are facing with regards to it, and how the communities are at risk, and what are the gender barriers that could be like affected or are in like playing a very critical role when we talk about adaptive capacity in that scenario. Next, please. So my research objectives are going to have the following components. Next. So the focus of my research are based on the following components while utilizing the existing data that we have collected. Next, please. So in that scenario, what we're doing is try to identify the extent of groundwater related challenges that we are facing in that particular area. So in this way, so our research is going to utilize the GIS-based risk mapping to rank associate those factors that are actually responsible for this vulnerability. And we're just trying to also map out and review the action plans which are actually supporting the addressing the climate change induced vulnerability related to the groundwater. Next, please. So my research is going to indicate that what are the climate challenges, what are its rural implications when you talk about the communities, as also like indicated into it, and how we can integrate to come up with a kind of action plan with the proper water resources management while utilizing the satellite information, while utilizing the information that is being present that are being collected from the field directly, and how we can do a kind of monitoring assessment for the future like sustainability analysis. Next, please. Next. Next. So this is like the overview about my study area. So we have chosen the area of Okara. So this area is well known for its diverse variety of crops, and this area is also lies interflow between the two major rivers of Pakistan, which is Ravi and Satluj. And agriculture is a primarily economy activity in this region. Next, please. But now this area is like prone to the groundwater challenges, and there are various factors, and the land change pattern is also one of its factor, which actually relevant to from the past few years for the overexploitation of groundwater usage. And geographically, this area is vital for driving the baseline indicators for the land use change. And there is actually the need for developing the kind of strategies for the sustainable groundwater management in this area. Next, please. So the data collection that we have been done for this study is we have utilized the extensive data sets. So firstly, from the spatial Earth observational data sets, we have utilized the Landsat time series, and due to its good temporal resolution. And then we also integrated the kind of existing land cover atlases that exist, and we're also trying to implement the climatic parameters, how the precipitation is been changing in this area. So what is the temperature is going on in this area, and what is the quality of soil, and how it is linked with the land use, land cover. And most importantly, what we have done is kind of collecting the information relevant to the groundwater tubes, where it exists, what are their distribution, and what are their operational time and during different seasons, and what could be the discharge of using those tubes for the agriculture practices. And most importantly, from the field observations, we're taking the farmer perception, what they think, how the climate change has been impacting to their area as well. Next, please. So this is the kind of like the ground truth survey we have been conducted, and I've been a part of it. We're just trying to collect the information about the groundwater table depth, how it's declining from the past year. I'm just trying to geotag the cropping area where it exists, and we're actually trying to have a discussion with the community, especially the female farmers, how their actually role exists in terms of while making their decision in water and agriculture as well. Next, please. So we also trying to indicate what are the constraints specifically the female farmers while they are where actually they are facing, and what are the factors that are actually limiting their capability or the capacity while we talk about the decision making in agriculture and water. Next, please. So this is like some of the spatial representation of the data sets that we have utilized. So the left panel is indicated that the variation in groundwater table depth, and the blue region is indicate that the area where is actually the declining groundwater we have been observing. And the right side panel is indicate that the spatial extent of the land use, land cover, where the green area is indicate, okay, this is the agricultural land, and what are the area where the tubal density is high, and how the quality of the soil is been changing in this area. area and how the topography on this region. And this is like some of the spatial representations of the spatial, a few of the indicators that we have used for the kind of our further variability analysis. Next, please. So what we did is we actually combined all those factors relevant to the groundwater and associated factors, and we have done a kind of variability analysis so that we can get some assessment. Okay, this is the area which is actually facing the kind of variability in all these parameters. So this is the area which is where the actually groundwater is depleting in a very fast rate. So we actually combine all these factors, including the what we get from the ground truth and what we get the satellite, and we pass through the kind of variability matrix, and we come up with the kind of hotspots, which indicating, okay, this is the area which needs to be prioritized. Okay, this is the area which is more prone to the groundwater depletions, and this is the area which needs to be prioritized for the future action plan. Next, please. So when we talk about the results and finding, okay, this is the kind of spatial vulnerability risk assessment. So we came up actually the kind of, okay, the areas which are actually facing the highly groundwater depletion rate, and where the tubal density is high, where the table declining is a very fast rate from a past few years. And we have like come up with the results that the 35% of this area of Okada, okay, this is the area which is facing severely groundwater challenges, and 20% areas it shows, okay, this is the moderate to moderate to a low area. Okay, this area is maybe like sometimes don't need to be prioritized for the further action. So our finding is actually providing support to the, especially to the agencies and relevant to the water sectors, in a way that they can do a kind of implementing strategy for safeguarding their groundwater resources, and they can promote a sustainable utilization in that specific area. Next, please. Okay, this is the kind of spatial distribution that we have made from the last 10 to 15 year, how the agriculture pattern is being changed and where are the crops they exist. And we have come up with a kind of, okay, 6 major crops is indicated in this area. And we have done a kind of phenological cycle. Okay, this is this signature, or maybe this phenological cycle is correspond to this crop. And we come up with a kind of final, our detailed crop based land cover. Next, please. Okay, so our key results is actually indicated majorly the change in a land use land cover pattern, which was recorded to reduce significantly between 2000 and to 2022. So it was like reduced from 91% to 80%, and further to it, we have observed the increase in the built up area. And when we talk about the gender descript priorities, yeah, it actually exists. So in that purpose, we have did a kind of baseline assessment and the baseline survey in that area. So we come up like, okay, the 2% are the ratio of the women, they are engaged in decision support, they are engaged in decision when we talk about the, okay, the agriculture, water, they are participating somewhere in this. So our like funding is also providing the preventive measures for the vulnerability information into the policy decision making process that require the special protection. Next, please. So what we're doing in that regard, so after the hotspot analysis, so we actually mark those areas where we have started deploying the groundwater monitoring sensors, so at least we can get the real-time information about the water table depth, its conductivity, water conductivity, temperature, as well as its pressure, hydraulic and the atmospheric pressure. So at least we also made a like equal dissemination so that we can cover the overall area, but the red regions are very important to us, and we also actually try to make it more prioritized for the installation of this sensor. Next, please. So in the end, what we are doing is a kind of developing the comprehensive information, whatever we collected in this area about the groundwater tube wells, their tagging, where they exist, and how we can combine, how we can synthesize the information coming from the CTD divers, which is ground monitoring sensor. So we're developing a kind of comprehensive groundwater management information system. Next, please. So this is one of the screenshot of the GMIS system where I'm working on. So what we are doing is trying to synthesize the information, whatever it's coming from the groundwater tube wells, what are the agriculture tube wells, where it exists, what are their time, either they are operating on ignition, electrical tube wells, and what are they what are the distribution of drinking and industrial tube wells. So actually we are still in a process to getting into the information, and we're trying to incorporate this information into this dashboard. And we also like now in a phase for getting the information relevant to groundwater quality. Okay, where are the areas where the arsenic hotspots exist, and how we can prioritize all those areas. There is actually need a kind of action plan for the safeguard of our groundwater management information system. So next, please. So our way forward and new insight. Next, please. So in New Insight, we actually did a kind of comprehensive assessment combining both the qualitative and quantitative information. Okay, we did the focal group discussion, we did the ground truth surveys, as well as we try to had interviews with the communities directly, and I'm a part of it. And this is something that we're coming up with the kind of the vulnerability assessment, and it's a way forward. So next, please. Okay, so in way forward, we are looking into like this is like the major four component where we're looking it. In terms of policy implications, we are looking into their impact to the local communities and the well-being of it. And secondly, we are also looking the adaptive capacity in terms of women empowerment, how we can build their capacity where they think they don't have the resources to the specific capacity building programs, where how we can empower them, how we can encourage them to come okay to participate in it. And in terms of land, climate change adaptation is also like one of the factors where we're looking into it in terms of way forward. And then we are doing a kind of similar studies to those areas which are facing similar challenges. For example, we are trying to replicate the area where we're working on in Punjab. We're trying to replicate it from the other district. So this is the kind of like the information so that we can develop for our sustainability of our groundwater, at least development through developing these dashboard systems. So I think that's all. Next, please. Thanks everyone for your attention.
Thank you, our first presenter. The first presenter was Hafsa Aman, who is working with the Senior Research Officer, Geomatics at International Water Management Institute, IWMI. She is pursuing a PhD degree in photogrammetry, remote sensing from Wuhan University, China. And now is the time for questions. If there is online questions, please. Okay, thank you. I've been told that the questions will be at the end of the presentation of this session. So please welcome the second. Okay. The next presenter is a lady from Tunisia. Her name is Badia Cheli, a Water Research and Technology Center. But she will introduce more herself when she starts speaking. Welcome, Badia.
I can use this one. Okay. Good morning, everybody. Good morning, everybody. I am Mrs. Badia Chouli from Tunisia. I am working in Water Research and Technology Center that belong to Carthage University in Tunisia. I am a teacher and researcher in this center, Water Research and Technology Center. I am hydrogeologist. Today, I will talk about, in my topics, I will talk about the use of space technology for water management of transboundary groundwater sharing between Algeria, Tunisia, and Libya in North Africa. Yes. You have to go to that computer. When you click the computer. I should go there. Right. Just assign that computer. This computer, okay. The aquifer that I will told about, it is the Northwest Sahara Aquifer System, is called in French SAS project. It is aquifer, underground aquifer and fossil aquifer composed by two superposed aquifers, the continental intercalaire and the continental intercalaire, the complex terminal and the continental intercalaire. It is an area about 1 million kilometers cube shared by 3 countries, Algeria, Tunisia, and Libya. The population in this area is grow about 4 million in 2000 to 8 million in 2030. It is irrigated land and intensively exploited resources. It is a fragile ecosystem and very vulnerable environment. Here you have the survey of exploitation in this aquifer from 1916 to actually the number of the water points increase, and it is about 9,000 sharing between Drel, Well, Spring, and Fugara, and shared between these 3 countries. This project, or the SAS project, is hosted by OSS. It is Observatory or Sahara and Sahel Observatory, Observatoire du Sahara Septentrional, sharing between these 3 countries. The Sahel and the Sahara and the Sahel Observatory is a solidarity platform. Platform in the service of sustainable development in Africa, is a Tunisian based international and intergovernmental organization established in 1992. OSS action is focused on 2 major topics, land and water. It's for environmental monitoring, especially for desertification and water resource, in particular shared water. The project, or the SAS project, is implemented by different phases. The first phase is start in 1999 to 2002. And especially in this phase, what we do, the establishment of the common-based database, the development of the information system, and the construction of the conceptual model. And we try to make common data from all the scientific do research in this area, using all the approach, the geological approach in this area. Then we do modeling. And the second part, it was installation of the consultation mechanism between these 3 countries. Here, example of the The simulation modeling that I do for the continental intercalare to see the artesianism decrease from 1915 to 2015. The simulation model based in the model allow us to mapping vulnerable map that you can see the zone more vulnerable, and it is what you can focus the more study in this area. The second phase is concentrated in the estimation of the diagnostic of the agricultural practice in the SAS, and the setting up the institutional consultation mechanism between these three countries. The third phase is structured around the two main components: the socioeconomic study. The objective is the analysis and understand the irrigation behavior for the irrigator in this for a better valorization of water resources. And the second phase, it was demonstration pilot to try to make and accessibility of technical innovation in this area, and to implement or to introduce a new technology for irrigation. The first phase, actually, we try to use the remote sensing as approach between, this study is a new project between OSS and the Regional Center for Remote Sensing of North Africa states. It's implemented in Tunisia, and in cooperation with our center, Water Research and Technology Center. The main objective, or the general objective of this study, is to use Earth observation-based technology to help in management of internationally shared aquifer, to support national user organization responsible for water resources, develop and demonstrate products responding to the need of user, integrate aquifer product with user working context and procedure, train user in use, application, and limitation of remote sensing based information, and perform know-how transfer and cooperation with national remote sensing agency. The main products to answer for this objective, we start mapping the land use and land cover mapping and change detection. The objective is defining the common classification system for land use and land cover, and typology of their change between two dates, for example, 1919 to 2000. The application is land use and land cover information and temporal change analysis related to water resource management. Also, we try to mapping the rainfall estimation and evapotranspiration and water balances. Donc, the objective is the use of low spatial resolution and very high temporal resolution to elaborate mapping of the rainfall estimation and evapotranspiration and water balance. The entry or the application is daily monitoring of precipitation and evapotranspiration, seasonal monitoring for water balance, and evaluation of groundwater recharge capacity. Also, we try to map the water and vegetation monitoring in the basin, use medium spatial resolution and high temporal resolution to monitoring of vegetation and large water body, and monitoring of the evolution of the biophysical parameter that describe the status of the cultivated and natural vegetation. Donc, the intérêt is daily and seasonal monitoring of vegetation. Also, we are mapping the digital terrain modeling and derived product. The objective is to use the radar data to create DTMS and elaborate derived products such as contour map, slope map, watershed, and sub-watershed map. The interest is to produce two products of allometric data and elaborate of watershed and sub-watershed map and flow map. Also, we are mapping the water abstraction and irrigation. Produce map showing water abstraction and annual crop irrigation consumption using the aquifer land use and land cover map. The application is identification of water over consumption and detection of illicit abstraction. Then we are mapping also the surface water body and inventory and monitoring. The objective is to employ the radar image and optical satellite image to produce water body inventory map and the time? Yes. Oh. In conclusion, the consultation and institutional benefit from using Earth observation system for shared aquifers is visibility of map data, facilitating data exchange and availability, provide transparency, facilitate the consultation of decision makers. Thank you very much for your attention.
Thank you, Badia Shelley from Water Resource and Research Technology Center, Tunisia. The next speaker is Elizabeth Guzman from the Ground Specialization Department of the Faculty of Engineering at the National Autonomous University of Mexico. She'll be sharing insights on cloud computing and remote sensing data for potential groundwater recharge estimation, and is important in water resource management in Mexico Basin. You're welcome.
Thank you very much for the invitation. It's a pleasure for me to share with you these results for the pilot project in the Basin of Mexico. I think I don't have the control. Okay, thank you. Okay. Okay, so this is the content of my presentation. I'm going right to the introduction. So understanding the potential recharge is crucial for managing groundwater resources. In the basin of Mexico, most of the natural recharge occurs in the highlands. And this water recharge feeds the aquifer. So population settled in the basin highly depends on groundwater, extracting 2.5 times more than the natural recharge. Recharge estimations are variable and few, ranging from 36 to 172 millimeters per year. So one challenge lies on preparation and processing of data sets in a specialized software, which require users to have a specific training. And the other is the lack of information coming from stations on groundwater. So this project aims to investigate if global satellite data can be a viable alternative for estimating potential recharge in the basin of Mexico and other areas. And in this case, can the large amount of spatiotemporal data and computational resources be addressed to recent advances in cloud computing services? This is the reference model that we use to compare with our data. It was reported by González Ortigosa last year. They used the soil water balance model from the USGS, which is a quite comprehensive software able to integrate almost all parameters involved in infiltration, such as, of course, precipitation, temperature, land cover, soil type, topography, geology, etc. The model is based on the Torway Mather model. They calculate the soil moisture at a given time t, which is a function of the previous time, and the water inputs and outputs, like rainfall, run-on, runoff, interception, etc. So they configure these 4 models where we can see that recharge is around 200 millimeters in the highlands to the south of the basin. They have 0 values in red in the center of the basin. And they have low values to the north of the basin and around 1 to 10 millimeters per year. So this is the methodology that we use. We use 4 steps, basically. It consists on the first one, we calculate the moisture at field capacity and the wilting point from this open map product, which is sand, clay, and soil organic carbon content. In the second step, we eliminate the urban areas from this MODIS product. In the third step, we do a temporal resample of chirps precipitation and terranet evapotranspiration. We set them both to monthly scale. And these are input parameters for the Torway Mather model that we use, in which potential evapotranspiration is compared against precipitation. When potential evapotranspiration is greater than precipitation P, there is no recharge, but potential water loss. In the other case, if precipitation is greater than that potential evapotranspiration, water begins to accumulate, but there is no recharge because the saturation point is not reached. So this water comes for the next step. And in the next step, the saturation point is reached. So the recharge is calculated as the surplus of the precipitation. So the model is implemented in Google Earth Engine through Google Colab. It runs like any Python code, and it requires 2 values. One of them is the average routing depth that we obtain from this product at 0.2. And the other value that the code needs is the initial and the final dates of interest. So these are the results of the model, the average potential recharge map for the basin of Mexico in millimeters. So we can see in this map a similar distribution compared with the reference model in the in the southern part. This is the map of the potential recharge. In the southern part of the basin, we have values around 200 millimeters per year. In the central part and to the north, we have low values. In the left table, we can see the special average potential recharge for the entire basin in the first line, and for region. In the central columns, we can observe the values reported by González Ortigosa, our reference model, and in the last two columns are our values. So we obtain as an average potential recharge a value of 47 millimeters per year, compared with 45 from the reference model. A very similar value. However, when we compare or look closer to the subregions, we can observe important differences. For example, in the aquifer number 1, 2, 3, and the number 6. So now we are going to look closer to the aquifer number 1. The aquifer number 1, this is the time series in red. So we can see that the events of recharge have similar periods compared to the reference model, and we obtain an average of 151 compared with 76 of the reference model. So this is due to the routine depth that we use, which was 0.2 meters for the entire basin. Then what we do was changing the routine depth to a better value, more proper for the highlands, 2 meters in the forest areas. So we obtain a better time series, an estimate of potential recharge in average of 71 compared to 76 of the reference model. And this is the total series doing this change for the entire basin. We obtain at the end with this change in the aquifer number 1 at 36 millimeters per year compared with 45 of the reference model. Now the discussion is about 2 points. And at the beginning, we were expecting that the results were extremely different compared with the reference model, mainly because we didn't integrate runoff. So we checked the runoff for the basin of Mexico, and it turns out that is very low. As you see in the first map, the values of runoff is very close to 0. So that's why the model is working without integrating runoff. And in the second point of discussion is the arid areas. While we reduce the thickness of the soil, we try to force the model to increase the recharge, but it doesn't work. Then we didn't get a good fit of the model respect to the reference model. At the end, we obtain a potential recharge of 8 millimeters per year and against 25. So this is a limitation of the model. In arid areas, another mechanism should be considered. And our low outlook, well, since we observe a significant dependency on routine depth, we are planning to integrate this product that seems to have better routing depth for the area. Other plan that we have is look the potential evapotranspiration that seems to be overestimated on the arid areas. And the other is integrate, of course, the product of runoff, where the where in the areas where is the runoff plays a significant role. And the last one is where we would like to try the product and see how is the potential recharge over time in areas affected, for example, by deforestation, land use, or wildfires. Okay, your conclusions is that the model is consistent with the reference model. So we need only to integrate the runoff product. That we need further investigation in arid areas. And the last one is about our experience in cloud computing services. It was easy and immediate access to results. So we think this could be a tool that may have application in water resource management. These are our references and our contact in the university. Thank you very much.
Thank you, Elizabeth. We have an online speaker, Mr. Amos Kaboba from the University of Energy and Natural Resources, Ghana. He is currently co-chair of the Program Board for Group Earth Observation, GEO, and Land Degradation, Neutrality, Flagship and Dean, International Relations Office of the University of Energy and Resource in Ghana. He published 80 plus articles in reputable journals of the application of satellite technology for water management in Ghana and Africa. Welcome, Mr. Amos Kaboba.
Yeah, thank you very much. First, I hope you can hear me from there. Do I have to share my screen?
Mr. Amos, you have to share your screen, please.
Okay. Okay, you can see my screen.
Can you adjust it? Mr. Amos, can you hear me?
Yeah, I can hear you.
Can you make it?
Sure,
Can
you can see my screen.
Can you make a full of it, please? It's okay. It's okay. Proceed.
Now you can see my screen. Okay, so I hope you can hear me. So this this morning in Costa Rica and afternoon where I am in Nigeria now. Greetings and thank you for the organizers for giving me the chance. So today I want to share some highlights on some work which has been done in Ghana, and this is contributed by other authors which are stated here. Now, I want to start by saying that there is a region in Ghana which is called the Afan Plains. This is a very important region in Ghana because it is also more like the agriculture hub of the country, but there is heavy dependence on groundwater. And you also find out that the population growth in this area is on the increase. So there has been a need to think about how can we start to look at groundwater issues in this particular area. Now, one thing you will realize in this area is that sanitation is a major problem. So you have sanitation problems, you have issues of agriculture also happening in this same region. And you also have what I call poor siting of latrines. So if you juxtapose this with your groundwater resources, it means you need to really think about issues of vulnerability. So this inspired the work that we have been trying to work on. So in trying to undertake this work, we try to adopt two methods. Now, one method is called drastic. So the drastic more or less uses the normal, let me call it AHP kind of weighting system to collect. You take different parameters and you weigh them using the AHP system, and at the end, you make a decision based on the outcome. Now, in our part of the world, getting all of these drastic parameters are always very difficult because, one, you have cases whereby boreholes are drilled and pumping tests are not conducted, and this information is just not available. So we try to develop a simplified model, which is called the F-Hydra model. So in this particular case, we try to look at how are the results like if you compare the two in assessing the water, the groundwater vulnerability situation. So you will see here that the results which are coming from the drastic is indicating that roughly 30% of the area is highly prone to vulnerabilities. And you also see that these areas are much closer to the water bodies. So this is what the drastic model is showing us. By the way, the drastic model is a widely used model in groundwater vulnerability. And if you Google it, you find out that quite a lot of work has been done with that. So now when we compare that to the F-Hydra, then we start to see that there is some kind of a disparity between the results. Because in the case of the drastic that is giving us 30%, the F-Hydra is giving us only 1% high vulnerability. But again, when you look at in terms of decision, looking at, for example, which areas are moderately marked in terms of the drastic, you find that the drastic is estimating roughly 50% of the area as being areas that communities or government needs to start to think about something. But when you come to the F-Hydra, it's also indicating roughly 50% chance that these areas will need to give some kind of indication as what to be done. Now, we have published this work, and if you are interested, you can look at Ajari and tell one of my students that we work together on this work. But this is work that is still ongoing. We are still collecting more data to see how to validate this work over the whole country. Those results are not ready yet, and once they are ready, we will continuously update this. But what I'm trying to emphasize in these two scenarios is that in Africa, we realize that there is a need, and especially in Ghana, there is a need to start to think about how can we sometimes simplify very complex models to simple ones that we can be able to quickly provide decisions for the people who are involved in the management of water resources, especially in this case. So in this particular one, when we had the results, so we discussed with what we call the NGOs that were involved, the African Plains Development Organization. Then we also engaged the municipal assembly, and we sat with them and said that, okay, this is what our maps are showing us, and hence there was a need for the communities to come together in order to start to provide some kind of measures in trying to safeguard and protect their water resources. So as an ongoing work, so at least this graph here is just showing the comparability between the two, which I have explained. So the disparity comes in the high side in terms of the vulnerability. And again, the weakness for the FR is that, of course, we are using very limited amount of parameters in order to estimate that. So, but the point is that we are still looking at this to see how best we can still improve the results in order to provide maybe a much closer to the drastic, which is widely known. Now, as an ongoing work, we decided to go to this same place and try to adopt, in addition to what I call the potential, in this case, we try to look at what are the groundwater potential zones. It's still in this particular area. And in order to do that, first we use the AHB to do that. So we use the AHB method in order to estimate what were generally the groundwater potential zones. So you will see that generally, of course, you have a lake, so the lake areas will generally show you high potential because water is always stored there, so your recharge is always closer. But you will see that there are a lot of areas which are a bit mountainous areas, hilly areas, that are showing low possibility. Then we went further to apply a SWOT model. This is what we are still working on. We are still trying to work around this. So we apply a SWOT model to further see, for example, what are the potential recharge areas and what have you. So the need for this is to help us to understand with the vulnerabilities and with the potential recharge zones, is there a midway somewhere between drying up of boreholes or some kind of pollution, especially the fact that you have agricultural activities and also quite a number of the siting or latrines that are all sometimes not sited in a way, in a good proximity to the boreholes. So this is what we are still working on. And we hope that with the SWOT simulations, it is generally showing that, of course, the groundwater recharge is increasing. It increases just as, of course, when you have the rainfall also, because the rainfall is a main recharge, because in Ghana, we are not really doing artificial recharge. So it's all being done by rainfall. So in terms of summary, what we are trying to push forward with this work is that groundwater, because it's an unseen resource, it's a resource which is hidden from us. It requires a lot of effort, a lot of collaboration, and I'm happy to listen to the presentation from Tunisia, from all the other people who have presented. I think it presents a room for us to discuss methods, methodologies, and to share knowledge to see how continuously we can collaborate together, research on it, and based on that, share our tools, and as a result, provide a midway by which we can be able to continuously monitor this critical resource, especially in Africa, that we are heavily dependent on groundwater for water supply. So on that note, I wish to thank everyone for listening, and to all my co-authors who have also contributed to this, and to the organizers and for Costa Rica for hosting this place. Thank you very much. Looking forward to your questions.
Thank you very much. The next speaker is from Bolivia. We'll be discussing on assessing of interaction between land use change and groundwater recharge and urban heat island remotely sensitive signature in Santa Cruz. Anne Rodriguez, please, it's your turn. Yes, online. Oh.
Good morning. It is a pleasure for me to be part of this important conference. My name is Ana Rodriguez. I am from Bolivia in South America. I am here to present the following research: assessment of interactions between land use change and groundwater recharge under urban heat island remotely sensed signatures in Santa Cruz, Bolivia. First of all, let's talk about the term urban heat island. It is used to describe an urban area that is warmer than the rural areas that surround it, and describes local scale temperature differences. The main cause of the urban heat island is urban development. Urban areas are often covered with asphalt, which prevents water underground from evaporating. Now, my first task today is to show you how I have identified urban heat island signatures using data from satellites. The next task is to show you why satellites are useful in countries with scarce resources to monitor environmental variables in cities, especially in Latin America. Then I will show you some impacts of heat in tropical cities like Santa Cruz. To begin, I have to say that last year, media has put attention on this issue because reports indicated that at least 7 people has died because of heat stroke during the month with the highest temperatures registered in Santa Cruz. But not only people was affected. High temperatures affected also livestock production. For example, poultry and swine industries have been seriously affected, facing important economic losses. Now, my question is, considering that Santa Cruz relies completely on groundwater for drinking water supply, how is drinking water supply affected? That is my research about. At this time, I will show you my concerns over a city of 1.2 million people located in central western Amazon. For this purpose, I have used data accessible to the public from the Modis Terra platform. I have used land surface temperature from year 2000 to year 2023 from an area affected by an aggressive and unplanned urbanization processes affecting the Amazonian forest. Well, one of the consequences of land use change and forest loss is the surface energy alteration balance, which in turn alters the surface and subsoil water balance. In this case, I will try to demonstrate that drinking water supply can be affected. Look at the figures in the upper part. I am comparing the imagery from year 2000 on the left with imagery from the year 2020 on the right. The two images show the dramatic impact of unplanned urbanization in a city located in the Amazonian region. The following figures show the impact of such change in land use. Comparing on the left the land surface temperatures measured by the satellite in the groundwater recharge zone affected by land use change, and on the right the land surface temperatures in the city downtown. In this case, the temperatures in downtown are much higher than temperatures in the city outskirts. Here, the differences in temperatures are between 3 degrees and 4 degrees Celsius. which is enough to make a noticeable impact. An interesting fact occurs in the case of Santa Cruz, which is that land use change is occurring in one of the areas where groundwater recharge occurs. Well, about the results, let's say that sandy soils characterize the groundwater recharge zones with high infiltration rates. Then, when urbanization processes occur, soil become more compact, and in some areas, land are paved, reducing or blocking infiltration and causing an increase in surface runoff. Then, together with an increase in surface temperatures, which could be translated into an increase in evaporation, sum up to more losses for groundwater recharge, hence reducing water available for drinking water supply. To express the association between all those variables, I have calculated a simple equation in representation of the soil-water balance. The results are shown in the figure in the lower part of the slide. The interpretation of the figure is simple. Above zero, positive values, the soil-water balance indicated that groundwater storage will have a gain. For the contrary, when the soil-water balance is below zero, it means that water losses by evaporation are higher than that precipitation inputs, which means that there is less water available for infiltration and, for instance, to recharge groundwater reservoirs. The first aspect to observe is that here is no clear trend, neither upwards nor downwards. That is because precipitation does not have a positive or negative trend. In other words, precipitation does not seem to increase, but it does not seem to decrease either. Considering that precipitation is the most important component of the soil-water balance, groundwater recharge does not define an upward or downward trend. However, after urbanization processes intensified in the middle 2020s, soil-water balance gets altered. Seasonal changes are more pronounced. The number of months with high recharge seem to increase, but in other years, the number of months with negative soil-water balance seem also to increase. Then, a comparison between before and after 2010 defined different recharge dynamics. Well, about the conclusion of my research, I have to say that a general definition for urban heat island identification is to find areas with considerable higher temperatures than the surrounding areas. This definition applies in Santa Cruz, where downtown temperatures can be from 3 to 4 degrees higher than in the surrounding of the city. Because of that, I can say that satellite imagery has identified an urban heat island signature for this city in the Bolivian Amazonian region. Then, since evaporation is related to temperatures, both have increased in the last decade. Data also shows that precipitation intensity has increased. In consequence, the soil-water balance behavior has changed. The approach considered here indicates that soil-water balance has intensified. Months with higher infiltration are likely to increase, and also months with less water available from groundwater recharge may also have increased. In other words, the durations are wider and peaks are higher or lower, but are much different than it was before the urbanization processes, which become more aggressive since 2010. Given that also precipitations trends have changed, questions remain, or more precisely values, to understand how the future trends of water supplies will be in the future. So to conclude, I believe that there are many things that cities and communities can do to minimize the effect of heat islands. One of them could be for example, planting vegetation and trees, which can help increase evaporation that cools the surrounding areas. Additionally, using some new materials like cool roofs and cool pavements, and also and definitely with urban planning in order to make the cities better for the people who live there. So thank you to all of you, and I hope I have made a contribution with my research.
Thank you very much. We have a limited time, like 6 minutes. So please let us go for questions. We have 2 participants online, beginning with the first online from China, the Aman. Please, if there is any question.
Thank you so much for all the presenters, are very interesting research. I have a question which I was discussing with Elizabeth about the situation in Mexico City. I mean, I don't know if the kind of models that she's working with can be coupled with another model that can try to estimate how much the city of Mexico is sinking. For example, one of the effects that could appear from this dramatic 2.5 ratio between the amount of water that is being consumed and the amount of water that is being infiltrating or recharging the groundwater reservoir.
Is that for Elizabeth?
Thank you very much for the question. Yes, actually, we have in some areas a very sinking of the soil, because there are some layers at the surface where we have clays. So this material can compact very fast. So in some areas we have around 30 centimeters per year of the soil compactation. And another projects have considered this compactation of the soil, and the conclusion is that the thickness of the aquifer cannot be recovered. So it's going to continue sinking or having compactation, and the storage capacity of the aquifer won't be the same in the future. So the problem now is try to reduce the pumping from wells and try to increase the capacity of the city to capture the water that is running off over the city.
Thank you. Another question for the participants from online, please. We have two online waiting. Proceed.
Can I?
You want to ask question?
Yeah, I want to ask a question.
For who? Online?
No, not online, in
Oh.
person.
Okay.
So this question, good morning, everybody. This question is for Dr. Badrian, who talked about the transboundary groundwater management in the 3 countries. And you also talked about the institutional arrangements and how it is currently working. So I was just wondering whether there have been any conflicts, because you're talking about a kind of a transboundary resource. And you also talked about a mechanism in place. So are there any examples of a conflict, and how has that been resolved, particularly with the technology that we have?
Yes, as I told in my presentation, before starting this project, the SAS between these 3 countries, and it is this 3 countries is we install platform by OSS, Observatory of Sahara Septentrional. And this platform try to share all the information between these 3 countries, common data, common research, and try to make the transfer of the technology between these 3 countries. And I think there is, at the moment, there is no problem between these 3 countries. Yes.
Thank you. Another question?
Yes, thank you. I have a question for the first speaker, Hafsa.
Okay.
Hafsa, you talk about farmer perception, gender-specific vulnerability, and also at the end about ground truth service. I wanted to know if you consider a way to spatialize this information in order to combine somehow with the different geospatial information, the different inputs you used in your vulnerability study.
Yeah, okay. So first of all, I think thanks for the wonderful question. So about the ground truth surveys that we have done with the with the farmer community. So what we have identified is if we look into the geographical locations of the farmers, where they're actually impacting most from the groundwater challenges. So actually we're trying to have a kind of discussion with them. So like how much the crop productivity in that regard is been changed from the past year, yes or no. So if their answer is giving us a yes, okay, so we start putting them in a very into a like high risk factor. And same like for the in terms of the gender like discrepancies. So when you start like the engaging with the farmer females, especially the one with the progressives, so actually we have made a kind of questionnaires specific to the locations that we are doing a kind of survey. So we're collecting the information like either how much they are actually involved in those kind of activities, and how much they're engaged, and what they think that in terms of decision making, where they categorize themselves. So whatever the information about this challenge we have gathered, so we actually put all those information into the certain criteria in terms of exposure and risk. And but again, geospatially, what we did, so we actually map out all those locations. We have actually did a kind of survey with the communities. So then we in the final we come up with the kind of geographical locations. Okay, these are the areas where the farmers are highly susceptible to the kind of exposure in terms of the agriculture productivity. Okay, this is the area with the gender or the farmers we actually met with the female farmers. They are actually suffering a lot. So this is something we have been carried out. And secondly, about the ground truth survey of the groundwater. So in that way, what I did actually, we have been engaged with the different government agencies, And we are trying to get the information initially on a very manual basis. Okay, it was a kind of blower method. So it was a kind of a wire, and we start putting into the ground. And whenever it touched with the water surface, then it gave us a kind of sound of sound of something. Okay, this is the water level. So this was the kind of like initially we made a very manual effort for the groundwater table calculation. So then we made it very like automatic when we started installing the CTD divers in those areas.
Thank you very much. We have a question from Amos Kaboba online. Amos? Amos online? Not connected. Another question, if there is any, if time allows.
Thank you. Good evening. This is a question for Badia. I would like to ask her if you can explain a little bit with more detail the significance of remote sensing for water monitoring in your study area.
I think the use of Earth observation in our area can help to mapping in large area, and you can get specific maps like I show you for the DTM and evapotranspiration. You can get also the very specific and very validate and precise data for using in this project for sharing water.
Thank you, Badia Shelley. Amos is back. Amos online?
Yeah,
You have a question? Yes. Okay, Amos, I think has lost. So what's the time now? So as we have heard the session, we had a very interesting presentation. Thank you for the participants. But we have seen in the space technologies that it offers a powerful tool in monitoring groundwater resources around the world. And this has been evidently proven by the following relevance in remote sensing, in geographic information system, and also in global positioning system for precise location, and also the benefit we have seen from the space technology under the water, groundwater in many resources. It covers a large area in monitoring, especially when you have a real-time data, and it is cost effective, and it is a time less consuming when you do the acquisition. Also, conclusively, I can say that the space technologies has rationalizing groundwater monitoring, which provide the variable insight for better management in water, especially in the regional level and the government level, and also the district ones. Integrating space-based data with the ground observation also had led the holistic understanding between the water managers and also the stakeholders. Though we had some gaps, everybody had discussed this concerning about the data access and quality, also the technical capacity. Most of the people seems like they don't have the technicalities to run the process, and also integration with the different data sets like the areas, some of the areas has a different coordinate system maybe, or sometimes they don't have cause stations, the continuous one that can easily make the data acquisition, especially in the traditional method, run properly. Therefore, I can recommend maybe we have an international collaboration between the expertise, the managers, the water resource managers, the stakeholders, and other expertise concerning about the water resource management. And also capacity building, whenever happens, please let us share in order to enhance the ability on keeping this water resource sustainably. Also, the last one to conclude, but I think sometimes other countries might have the improvement in standardized portals or river protocols in the way of accessing data that can simplify the analysis as well. Therefore, when we are going to have a break, please let us have a space.